Okay, this video covers using the trigonomic identities. Now there are several ways to use the trigonomic identities, and we're going to talk about a couple of those today, and then future videos will address some of the others. All right, now here are the fundamental trigonomic identities. The first ones are pretty basic. We have these tangent is sine over cosine, secant is 1 over cosine, cosecant is 1 over sine, and cotangent is the reciprocal of tangent, so it's 1 over tangent, but it's also cosine over sine. Now these in general are called the reciprocal identities. They're actually pretty easy. We know that sine of theta is equal to the reciprocal, or 1 over cosecant of theta. And then we know that cosecant of theta is equal to 1 over sine of theta. Again, the reciprocals of each other, so that's pretty easy. Likewise, cosine of theta is 1 over secant of theta, and then secant of theta would be 1 over cosine of theta. Again, all very, very easy things here. Lastly, tangent of theta is equal to 1 over cotangent of theta, which would mean that cotangent of theta is also equal to 1 over tangent of theta. Pretty simple there. Now, we also have the really extremely important Pythagorean identities. The main Pythagorean identity is that cosine squared plus sine squared equals 1. But this can be transformed a little bit, right? If we divide everything by cosine squared, we get this second form of the Pythagorean identity, which would be 1 plus tangent squared equals secant squared. We could also go back to the original one and divide everything by sine squared, which would create cotangent squared plus 1 equals cosecant squared. Now, a lot of kids think that they have to see this exactly like this. Understand that these Pythagorean theorems, they're equations, and as you follow the rules of algebra, you can't shift things around a little bit. For example, if I take this first one right here and I subtract 1 from both sides, I get that tangent squared of theta equals secant squared theta minus 1. All I did was subtract the 1 over. So again, essentially it's the exact same thing. I just maneuvered things around a little bit. So be careful if you don't necessarily see it in the exact same form. My hint that I always tell kids is if you see a trig function squared in a 1 nearby, it's probably a good chance you're going to be able to using one of the Pythagorean theorems or Pythagorean identities. Okay, so the first use of all these identities is being able to find all 6 trig functions with one given. So I'm giving you that secant of some angle v is equal to -3/2. I'm also telling you that tangent is greater than 0. That's going to play an important part because I need to determine what quadrant I'm in. So the first thing I'm going to do is I'm going to use the first identity, and that's that secant and cosine are nothing more than reciprocals of each other. So for cosine of v would be -2/3. Very, very simple, very easy to use the reciprocal identities. Now, if cosine's negative, cosine remembers x, that means x's are negative, I must be in quadrant 1, I'm sorry, take that back, quadrant 2 or quadrant 3. I got to be in one of those two quadrants if cosine is negative. But the fact that tangent is positive means that I must be in quadrant 3. The reason being is in quadrant 2, sines are negative and cosines, in quadrant 2, cosines are negative and sines are positive, which means tangent would be negative in quadrant 2. Well, the fact that I know tangent's positive, I must be in quadrant 3 where sines and cosines are both negative, hence a positive tangent. Now, let's continue on here. What do I want to find next? Well, again, go back to your trig identities and use whatever one you want. I'm going to use the Pythagorean identity that cosine squared of v plus sine squared of v equals 1. So let's see here. Cosine squared would be 4/9. Again, all I do is took cosine and squared it, and I got 4/9. Plus sine squared of v equals 1. Subtract the 4/9 over. Sine squared of v equals, let's see, 1 minus 4/9. That's 9/9 minus 4/9 is 5/9. And then square root, and I get that sine of v is the square root of 5 over 3. But because I knew from the beginning, based on what I was told that I'm in quadrant 3, I do need to put a negative on that sign. All right, now that I found sine, I could pretty easily find cosecant, because I know that cosecant is nothing more than the reciprocal of sine, which would be -3 over the square root of 5. Not a bad answer, but I don't really like that square root down there, so I will multiply the top and the bottom by the square root of 5, and I get -3 square root of 5 over 5. So there's cosecant. So let's see, I had secant, that was the one given to me. I found cosine pretty quickly. I got 2 more to go. Now, how do you find tangent? Well, I actually have a couple different options. I could take sine and divide it by cosine to get tangent, because tangent is sine over cosine, or I could come down here, since I know secant, I could find tangent because I know that, look, again, I already wrote this here. If I do 1 plus tangent squared, I get secant squared, which means tangent squared is secant squared minus 1. So I can come down and do that as well. So I know that 1 plus tangent squared equals secant squared. So once again, I know that 1 plus tangent squared equals secant squared. Secant squared is 9/4. So I'm going to subtract that 1 over, so that'd be 4/4. So I'm going to do 9/4 minus 4/4. Let me just write that out here. That's going to be 5/4. And then I'm going to square root both sides, and I get tangent, I guess I should have been using a v instead of a theta, is the square root of 5 over 2. I'm going to leave it positive because I knew tangent was positive. And I wrote tangent squared there, but now that I took a square root, it would just be tangent. And then now lastly, cotangent would just be the reciprocal of that, 2 over the square root of 5. And again, I don't necessarily like the bottom down there, so I'm going to multiply top and bottom by radical 5, and I get 2 radical 5 over 5. So that's a pretty quick, easy example. And I know I kind of ran through that pretty quickly, but for the most part, it's really simple to use those identities to find all 6 trig functions. So make sure you could do that. Pretty easy there. All right, the next thing we could do with these trig identities is to simplify expressions, okay? Now, simplifying expressions is a little bit tricky. There's several different strategies you could do, but the idea of simplifying is trying to clean up the problem. So let's look at some simplifying examples here. So I have 2 examples here. Here's the first one, and then here's the second one. All right, now with this second one, I'm going to use the first strategy. The first strategy you should always use is to turn everything into sines and cosines, because that's going to make things a little bit easier to see. So cotangent, I'm going to change to cosine of t over sine of t, because that's what cotangent is, times cosine of t. And then now what happens is I get sine of t plus cosine squared of t over sine. Okay, so is that simpler? Well, no, so let's keep going. What I'm going to do here is now I'm actually going to do what it says. It says to add, right? So I'm going to add. So in order to add, I need to get a common denominator. Well, my common denominator would be sine of t, right? So I need that common denominator of sine of t. This guy up here, he has a current denominator of 1, so I'm going to multiply top and bottom by sine squared, or I'm sorry, by sine of t. And that way I'll get that common denominator. Well, that's going to produce a sine squared of t on top, because sine times sine is sine squared. Now this guy over here, he already had my common denominator of sine, so I'm going to leave his numerator as cosine squared of t already. Now this is actually awesome, because what's left on top is a Pythagorean identity. Sine squared plus cosine squared is 1, so I could change that to a 1. And now I get 1 over sine of t, and I can use my reciprocal identity. 1 over sine of t is cosecant of t. So I was able to take this first statement that had 3 different trig functions, and I was able to reduce it down to just one simple trig function. That's the idea of simplifying. Now it does take a lot of practice to be able to see all of that, and that's what we're going to do in class. All right, here's another example right here. Sine of alpha over cosine plus cosine of alpha over sine. Well, everything is already in terms of sines and cosines, so I'm going to do what I guess the only other thing I could do is go ahead and actually add these together, right? It says to add. Let's go ahead and do that. So my denominator, my common denominator, would be cosine of alpha times sine of alpha. This guy has the cosine, but he needs the sine, so I'll multiply top and bottom by sine, which is going to generate a sine squared of alpha on top. This guy over here has the sine of alpha. He needs the cosine of alpha on the bottom, so I'll multiply bottom and top by cosine of alpha, and I get a cosine squared of alpha. Now, awesome, sine squared plus cosine squared is once again 1, so I get 1 over cosine of alpha times sine of alpha. And what I'm going to do is I'm actually going to separate this. I could treat this as 1 over cosine of alpha times 1 over sine of alpha, okay? And 1 over cosine is secant of alpha, and 1 over sine is cosecant alpha. So I get that this somewhat ugly addition of these 2 fractions was basically just secant of theta times cosecant of theta. For the most part, that's pretty easy. Now, just so you know, sometimes these simpling problems has a couple different answers. For example, somebody else might have looked at this problem and said, oh, I know the answer right away. Sine over cosine is tangent, plus cosine over sine is cotangent. So which one of these answers is more simplified? Well, I don't know. They both have 2 trig functions, so again, I would probably accept either one as correct. All right, let's take a look at a couple other ones here. These ones are going to get a little bit tricky, but they're actually not too bad. All right, so here's number 3 and number 4. All right, my strategy with number 3 here is, well, I could change everything to sines and cosines, but there's actually an easier way. When you have a single value, one value in the denominator, you could basically take your top and divide both things by it. I mean, this is just basic rules of math. I could take tangent of beta and divide it by tangent of beta, plus cotangent of beta divided by tangent of beta. And basically doing distribution with division, right? Tangent divided by tangent plus cotangent divided by tangent. I mean, if you go backwards, all I'm doing is saying I have a common denominator, let's add them together. So this makes it pretty easy because tangent divided by tangent is 1. And let's see here. Let's kind of work our way through what cotangent divided by tangent is. Well, let's see here. There's actually several different ways you could do this. One way is to say, okay, cotangent is 1 over tangent. And then instead of dividing by tangent, I'm going to multiply by the reciprocal of tangent, which is 1 over tangent, right? So I get 1 plus 1 over tangent squared. But 1 over tangent squared is cotangent squared, so I get 1 plus cotangent squared. And now, what is 1 plus cotangent squared? Well, I could once again use my identities, and you should actually recognize that. 1 plus cotangent squared is cosecant squared. That was one of our Pythagorean identities. So that entire value was nothing more than cosecant squared of beta. Again, kind of tricky, but you just got to get used to solving these problems. All right, check out this next one here. Sine over 1 plus cosine over sine. This is one of my favorite problems because it uses a lot of really cool strategies. The first is I'm just going to get a common denominator. So my common denominator is going to be 1 plus cosine of theta times times sine of theta. Okay, pretty easy strategy when you see a plus sign and some fractions. Let's go ahead and actually combine these together. Now on the bottom, I'm just going to leave that as that. Don't try to distribute that bottom, just leave it alone. Okay, this denominator right here needs the common denominator, so I'm going to multiply by sine on the top and on the bottom, which gives me a sine squared on top. That's pretty nice. Okay, this guy right here, this denominator needs the 1 plus cosine of theta. So I'll go ahead and multiply the top and the bottom by 1 plus cosine of theta. And let's see here, what's going to happen? Well, let's see here. I'm going to go and distribute. That's cosine times 1. That's going to be a cosine of theta. And cosine times cosine is cosine squared of theta. Okay, so let's see here. I'm going to continue to work here. On top, I notice something really cool. On top, I notice I have a sine squared plus cosine squared. Now, they're not right next to each other, but rules of addition say I can move things around a little bit. I know that sine squared plus cosine squared is 1. So I have 1 plus cosine of theta. So this guy and this guy made the 1, so I have the 1, and then the cosine of theta is still there, over 1 plus cosine of theta, all times sine. And then, whoa, wait a minute. I see a 1 plus cosine of theta on top, and I see a 1 plus cosine of theta on the bottom. Because those are both factors, I can cross those out. So on top, I'm left with 1, right? Because you got to remember, this guy is 1 plus cosine times 1. You got to give it a factor, right? A factor is something times something. So something times 1, I'll make that, right? It makes it easy. So I'm left with that 1 on top. On the bottom, I'm left with that sine of theta. And then 1 over sine of theta is cosecant of theta. So here's my final answer. So I took this pretty ugly value up here, and I got this nice simple cosecant. So simplifying is definitely a little bit tricky. Just kind of take your time with it and realize that you're just trying to use nothing more than algebra, basic rules, and the trig identities together to try to make these problems a little bit simpler looking.